Okay, so hello everybody and welcome back. Today we're going to be continuing our Chapter 8 lecture on conservation of energy. And now we're at the point where we can finally state the law of conservation of energy and try to figure out what it means. So the law of conservation of energy says that energy can never be created or destroyed. It can only be converted from one type to another type or transferred from one object to another object. Okay, so it can't be created or destroyed. It can only move around. So when we say energy can be converted from one type to another type, a very simple example of that would be if you drop an object from some height. So initially, it's all potential and no kinetic. But then as it begins to fall, it picks up speed and it loses height, it loses potential energy. So what we say is potential energy is being converted to kinetic energy as it falls down. So that's one example. Okay, we also say that energy can be transferred from one object to another. What's an example of that? Well, let's say you have two billiard balls on a pool table, and initially this one, let's call it ball number 1, is moving towards this one, ball number 2, which is stationary. So in other words, ball number 1 has kinetic energy, ball number 2 does not. So if they collide with each other, you can actually get a situation where ball number 1 is now stationary and ball number 2 is moving off to the right like this. So what just happened? Energy was transferred from one object to another. Okay, so those are things that can happen. Okay, but what can't happen is energy is created out of nothing or destroyed. That's the idea. So here's a question for you guys. It's sort of a conceptual thing. When you give an object a push so that it starts to slide across the floor, we know that in reality, it's eventually going to come to a stop. And of course, that's because of friction. So again, if you push an object so that it starts sliding across the floor, that's the initial state of your object, but the final state is that it's at rest. So we lost mechanical energy in this process, okay? So what happened to that mechanical energy that we lost? Does the fact that we lost kinetic energy violate this law that we just learned about? Does it violate conservation of energy? Try to figure this out, see what kind of answer you can come up with, and then we'll go through it together. Okay, so the answer to the previous question is no. It doesn't violate conservation of energy when you have a box sliding across a table and it comes to a stop. But to understand why, we need to realize that there are other forms of energy that we haven't seen yet, that we haven't learned about. So what we have seen so far is kinetic energy and potential energy. And we also know that if you add kinetic and potential together for whatever system you're looking at, that the sum total is called mechanical energy. But to be a little bit more specific, this is technically the energies of the macroscopic objects in your system. So when we talk about mechanical energy, we're referring to the energies of the macroscopic objects in your system, like things like a box sliding across a table or a wheel rolling down a ramp, things like that. One thing I want you to realize here is that if we look at a system on a microscopic level, and we see individual atoms and molecules, we have sort of a different picture. So in this animation that I'm about to show you down here, what we have is a container full of liquid. You can imagine this is water, and these are individual water molecules, okay? So even though on a macroscopic level, if you're just looking at a glass of water, it might look like there's no motion going on. But if you look at the individual molecules, you'll see there's a lot of motion going on actually, right? In other words, these molecules are undergoing random motions. They're jiggling around, they're bumping into each other, they're bumping into the walls of the container. There's all kinds of motion going on if you look at the system on a microscopic level. So we call this energy, the energy that these randomly moving molecules have, we call this internal energy. That's what this is called. So when we have a non-conservative force like friction or like air resistance that's doing work, what's happening is mechanical energy is being converted into internal energy. So in other words, the energy of macroscopic objects like a box sliding across a table is converted to energy of microscopic particles, which is what we call internal energy. But energy is still conserved. Okay, all that's happening is you're converting from one type of energy to another. So to flesh this out in a little more detail, again, let's say you have a box sliding across a table. Friction is acting on the box as it slides, and eventually the box comes to a stop. So the mechanical energy is all gone. We lost a whole bunch of mechanical energy. But if you look at the system on a microscopic level, you'll see that the box is made up of atoms that are jiggling around, and so is the table, and they're now jiggling around faster than before. They're moving faster than before. And what we say is the internal energy has increased. So we lost mechanical energy, but we increased internal energy. Overall, energy is still conserved. By the way, when we say the internal energy increases and the atoms and molecules that make up the table and the box are now jiggling around faster, we perceive that as heat being generated. In other words, that will quite literally make these surfaces heat up, and we can feel that if we touch the surfaces. And we know intuitively that when you rub your hands together, let's say, that's friction doing work. You can generate some heat in that sort of way. Okay, so up until this point, we've discussed in great detail over the last couple lectures the idea of energy, different forms of energy, kinetic, potential. We have different laws that govern energy, like the fact that energy is conserved. But you could take a bigger picture view of this and ask, what is energy in the first place? Like, what are we referring to when we talk about energy? So there's a quote that I want to give you by someone named Richard Feynman, who's a famous physicist that you may have heard of. And what Richard Feynman has to say about energy is this: there is a fact, or if you wish, a law governing all natural phenomena that are known to date. There is no known exception to this law. It is exact as far as we know. The law is called the conservation of energy. It states that there is a certain quantity, which we call energy, that does not change in the manifold changes which nature undergoes. That is a most abstract idea because it is a mathematical principle. It says that there is a numerical quantity which does not change when something happens. It is not a description of a mechanism or anything concrete. It is just a strange fact that when we can calculate some number, and when we finish watching nature go through her tricks and calculate the number again, it is the same. Okay, so what Feynman is trying to say here is that energy is sort of an abstract idea. When we say an object has kinetic energy, we don't mean that there's some kind of substance the object has. We just mean you can calculate some number, 1/2 mv squared, for that object and call it the kinetic energy. And then if you calculate all the different forms of energy that are relevant and add them together, that total energy just doesn't change. Okay, so it's not like energy is like a physical substance that moves from one place to another or moves from one object to another. It's just that energy is a number you can calculate, and if you calculate it again sometime later and you really account for all the different forms of energy, that number will stay the same. That's what we mean by energy being conserved. As far as what energy is, the best way to think about it is just a number you can calculate because it really doesn't refer to a physical substance or anything like that. Okay, so the next topic is mechanical power. So power is something we're all familiar with. Let me just give you some examples that you've undoubtedly seen in your real life. The power output of a car's motor. Okay, we measure that in horsepower typically. The power output of a light bulb, we typically measure that in watts. So, you might say you have a 60 watt light bulb, for example. All of these are examples of, in physics, what we call power, and it has a very specific definition. So we're going to get to that and talk about how to calculate power. That's what's coming next. Okay, so mechanical power is defined as the rate at which work is done. So it's one thing to say that, if I push a box across the floor, that I've done 100 joules of work. It's another thing to say how quickly I did that work. Did I do 100 joules of work over the course of 1 second? Or did I do it over the course of 1 minute? Those are very different situations in terms of power, because again, power is the rate at which we're doing work. So since it's a rate at which we're doing work, that can be understood as the derivative of work with respect to time, so dw dt. That's the definition of mechanical power. So the SI unit of power is a watt, which is defined to be a joule per second, because of course, we're going to have units of work on top, which would be joules, and units of time on the bottom, which would be seconds in the SI system. But we remember that in SI base units, a joule is a kilogram times a meter squared per second squared. And then this says we divide by seconds one more time. So overall, what we have is a kilogram times a meter squared divided by a second cubed. So this is what a watt is equivalent to when we break it down into the base units of kilograms, meters, and seconds. Okay, so that's mechanical power. It's the rate at which work is done. More generally, when we talk about power, not just mechanical power, it's the rate at which energy is being converted from one type to another type. So let me give you an example of this. The light bulb. The power rating of a light bulb is the rate at which electrical energy is converted to light and also heat within your room. Okay, so when we say a light bulb has a power rating of 60 watts, we mean every second that passes, we convert 60 joules of electrical energy into light and also heat that just gets spread out into your room. Okay, we're going to stick in this class to mechanical power, but I just wanted to make you aware that in general, power means the rate at which energy is converted from one type to another. But we'll stick to mechanical power. Okay, so now let's try to develop a formula for mechanical power. So let's consider an object that's moving along a path. Let's say we start here and we end up here. We just take this path to get there. And there's a force F being applied to the object as it's moving along the path. Okay, so let's take a look at a tiny little segment of the path, which I'll call dr, a tiny little displacement along the path, dr. For that tiny little bit of displacement, we know that the work can be thought of as the force dotted with dr. Okay, that's something we saw back in chapter 7. You can take force dot displacement. That's how you get work. And we're talking about a little infinitesimal amount of work, dW. So now we're going to apply the definition of power, where P is equal to dW by dt. And what we're going to do is just plug in this for dW. So I have F dot dr divided by dt. Let's write this in a slightly different way. Let's just move the F out to the front. So we have F dot dr dt. Now you should recognize this term right here. This is the derivative of position with respect to time, dr dt. Do you remember what the derivative of position with respect to time is? It's velocity. Velocity is what we define as dr dt. So in other words, the mechanical power can be thought of as the dot product of force with velocity. So you take the force, dot it with your velocity, and that is mechanical power. That's how it's calculated. Oops, let's go forward. Okay, so here's an example. Let's say we have a 55 kilogram box that's being dragged across the floor like this by a rope, which is wrapped around a motorized winch. So the rope is wrapped around this little winch here. The coefficient of kinetic friction between the box and the floor is 0.275, and the box moves along to the right at a constant speed of 0.375 meters per second. So we're going to answer two questions. What is the tension in the rope? So how much tension is here? And also, what is the power output of this motor that's actually moving the box along? What would be the power output in watts? So let's work each one of these out. Okay, so we'll start by drawing a free body diagram of the box. So what forces can we identify? We have the weight, and there's a normal force counteracting the weight from the table, pointing straight up like this. There's tension in the rope that's pulling the box to the right. And there's also kinetic friction, which is opposing the motion of the box going to the left. Let's draw a set of x, y coordinate axes to keep track of this motion. And then let's take note of the fact that we can say something about ax and ay, the acceleration of this box in the x direction and the y direction. Well, first of all, we can say ay is equal to 0 because there's no vertical motion. There's no motion in the y direction at all. So there's no acceleration in the y direction. But also ax is 0 because it moves across the floor at a constant speed. So if the speed is not changing in the x direction, we don't have any acceleration in the x direction. Okay, so next what we can do is F equals ma in the x and y directions separately. How about we start with the y direction? So the sum of the forces in the y direction equals mass times ay. So we have a normal force, which is positive, going up, and we have the weight, which is going to have a negative sign attached to it because it's going down. So we have N minus W equals 0 because, again, 0 acceleration, which is to say the normal force is equal to the weight in terms of magnitude, which is M times G. The reason that's useful, by the way, is kinetic friction is given by mu k times n. So we have mu k times mg for kinetic friction. So next we can do the sum of forces in the x direction, and that equals m times ax. Well, in the x direction we have tension, which is going in the positive direction, and we have kinetic friction going in the negative direction. So T minus Fk, that equals 0 because, again, we don't have any acceleration in the x direction. This tells us that T is equal to Fk, but we already saw that Fk is equal to mu k times mg. So we can calculate the tension. Okay, the coefficient of friction, mu k, is 0.275. The mass of the box, m, is 55.0 kilograms. G is 9.8 meters per second squared. And so what we're left with is 148.2. What are the units? Kilograms, meters per second squared. I'd want to keep 3 sig figs on this, though. So we'd round it to 148. And by the way, this unit is equivalent to a newton. So 148 newtons of tension. Okay. Now let's do the power output of the motor. So the motor is what's providing this tension force that pulls the box across the floor. So if we want to know the power, we would just take the force, again, which is the tension T, and dot it with the velocity. Okay. So what's the tension? It's 148.2 kilograms times meters per second squared. We're going to, here, actually, if I want to write this as a vector to show that it's going in the x direction, I'll put I hat. And then I'm going to dot that with the velocity, which again, if we want to show this as a vector, would be 0.375 meters per second. And then I would put I hat to also indicate that it's going in the positive x direction. So essentially what we have here is I hat dotted with I hat, which is equal to 1. And then we have 148.2 times 0.375, which works out to 55.57. And the units are kilograms. We've got meters squared on top. And then we'll end up having seconds cubed on the bottom. I showed you before that this is equivalent to a watt. So we'd also want to round the answer to 55.6 watts to 3 sig figs. And that's the power output of our motor, 55.6 watts. Okay, so here's one for you to try out. We have a crane that lifts a 1,500 kilogram load vertically upwards at a constant speed of 1.5 meters per second. Find the power output of the crane's motor in units of watts. Neglect air resistance and friction in the moving parts. Use this result we derived, that P is equal to F dot V, to solve this one. So pause the video, see if you can get this, and then we'll go through it together. Okay, for this one, we'll start with the free body diagram of the load. In which case we have two forces, the force of gravity, or the weight pulling it down, and the tension in the cable that's supporting the load. Okay, so those are the two forces. And we'll analyze them using this XY coordinate system where Y is going straight up. Now again, let's start by saying something about the acceleration. AY is equal to 0 because the load moves up at a constant speed. So it's not accelerating. And therefore, when we take Newton's second law, the sum of forces in the y direction is equal to m times ay. We have a positive tension force and a negative weight. So we have T minus W equals 0. Therefore, T is equal to W, which is equal to m times G. Okay. So the tension force, let's calculate it, is the mass, 1,500 kilograms, times G, which is 9.8 meters per second squared, which works out to 14,700 kilograms times meters per second squared. And again, we remember that this is equivalent to a Newton, but we'll keep 2 sig figs because 1,500 is given to 2 sig figs. When we calculate the power, that's the tension dotted with the velocity, because again, the tension is the force that the motor is providing to pull this load upwards. So we do T dot V. And the tension we just calculated is 14,700 kilograms times meters per second. Kilograms times meters per second squared, I should say. And to indicate that it's going upwards, we'll put a j hat unit vector right next to that. The velocity, that's 1.5 meters per second. And we also put a j hat unit vector next to that to indicate that the velocity is also going up. So you calculate these numbers and you have 22,050 units are kilograms. We get meters squared on the top and seconds cubed on the bottom. But again, we'll keep 2 sig figs. So about 22,000 watts is the power output of that crane. Okay, so the next topic is potential energy diagrams and equilibrium. So to introduce this topic, I'm actually going to start with a question for you guys, which is, let's take a look at the graph on the right. which shows potential energy for an object moving in one dimension. So the way this plot works is on the vertical axis, we have energy, and on the horizontal axis, we have position. And this red curve is showing us the potential energy as a function of position. In other words, U as a function of X. So for instance, if I pick a point X over here, I go to the curve, that tells me what the potential energy is at that position. Okay, so for each point shown, we have XA, XB, and XC. Determine whether the force acting on the object is in the positive X direction, the negative X direction, or equal to 0. So since we're asking something about the force here, I want you to remember that the relationship between force and potential energy is this. Force is minus du dx, so it's minus the derivative of potential energy. So based on that, you should tell me for each of these three positions whether the force is positive, negative, or 0. See if you can work it out. Okay, so we have a plot of the potential energy versus position. And using that, we're going to say something about the force. We're going to find out something about the force because the force is minus du dx. It's minus the derivative of the potential energy function. So remember what derivatives mean graphically. So a derivative is the slope of the tangent line to your curve. That's what a derivative can be interpreted as when we're looking at a graph. So I have minus the slope of the tangent line to the u versus x curve. That gives me the force. Okay, so at each one of these positions, let's say at point XA, what do we know about the slope of the tangent line? Well, you can draw it straight on the graph. Here's point A. The tangent line to the curve clearly has a negative slope. So therefore, the force at that point is positive because the force has the opposite sign as the slope. So the slope is negative, the force is positive. Okay, what about at XB? Well, we can draw a tangent line to the graph right there, and it's completely flat. So slope is 0. Which tells us the force at that point is also 0. Okay, what about at point XC? Over here. Well, we can draw another tangent line to this curve. This time we have a positive slope. And so therefore, the force is going to be negative. Because again, it has the opposite sign as the slope. So let's try to put all that together and kind of see what it's telling us. So here, at point B, where we see the potential energy goes to a minimum, we have 0 force. Okay, then if we're to the left of that, at point A, the force is in the positive direction, so to show it as an arrow, Fxa is just an arrow pointing to the right in the positive direction. If we're at point C, the force is pointing in the negative direction, so just have an arrow pointing to the left for Fxc. And that's overall what things look like. So if you have an object at point B, it's not going to feel any force. If you have an object at point A, it's going to feel a force that's pushing it to the right, so back towards point B. And if you have an object at point C, it's going to feel a force pushing it to the left, which again is going back towards that midpoint, point B. Okay, so here. You place an object a little bit to the left or right of XB, and the force brings it back to XB. So clearly there's something special about that point xb because the system kind of wants to be at that position. So what we call this point xb is an equilibrium point. Okay, and that takes us to equilibrium positions. So at an equilibrium position, the force goes to zero. That's the definition of equilibrium, is that it's a point where the force goes to zero. And so let's take an example of an equilibrium position. Let's say this point on our plot, which is a minimum of the potential energy. We saw in the previous example that this would be an equilibrium position where the force goes to zero. So let's imagine we take an object and we put it right here so it's at rest. Okay? So we place it at rest right at that point. So it's not moving and there's no force acting on it. So it's going to just stay there, right? If there's no motion and there's no force acting on it to push it one way or another, it's just going to stay there. Unless, of course, you had some kind of outside force that was pushing it around, right? So that's how equilibrium positions work. If you place an object there at rest, it's going to stay there until some outside force comes along and knocks it away. So the math behind this, of course, is that since the force is given by minus du dx, that tells us that if we want the force to be zero, du dx must be zero. So the derivative of the potential energy function is going to be zero at an equilibrium position. And so there are three different ways that can happen. Okay, we can have a minimum of the potential energy, okay, because the derivative certainly goes to zero at a minimum point. The derivative will also go to zero at a maximum. Let's say up here is a maximum in potential energy. But it will also go to zero if your potential energy is just flat and you're not talking about a minimum or a maximum. Okay? So these three cases we call stable. So at the stable equilibrium position, that's a minimum of potential energy. This would be a stable point. And we can think about the fact that it's a minimum by looking at the second derivative. So the first derivative is going to zero, but the second derivative is going to be something positive if we're at a minimum of potential energy because it's concave up. Okay? So second derivative is positive, first derivative is zero at a stable equilibrium point. Unstable equilibrium, again, that's a maximum of potential energy. That's up here. And so what we say there is the second derivative is negative because, look, it's a concave down shape. We have a negative second derivative at that point. If we have what's called a neutral equilibrium, that's the case where the second derivative goes to zero and you just have a flat function like this. Okay, so those are the three different cases we should be aware of and know how to distinguish between. Okay, so let's take a closer look at equilibrium positions and talk a little bit more about the difference between stable, unstable, and neutral equilibrium. So we'll start with stable. Okay, so when you have a stable equilibrium point, that's when you have a minimum in your potential energy function. So the reason we call this a stable equilibrium is that if I move the object a slight amount away from stable equilibrium, it's going to be feeling a force that brings it right back. So, for example, let's take a look at the left-hand side of the stable equilibrium point over here somewhere. The slope of this potential energy graph is negative, which means the force is going to be positive. The force in the positive direction is pointing to the right. Okay, if I'm over here on the right side of the stable equilibrium, the slope is positive. That means the force is negative. A force in the negative direction is pointing to the left like this. So that says, if I place an object over here on the left side of equilibrium, the force is going to be pushing it to the right, which brings it back here. And if I place it a little bit to the right, the force pushes it to the left, bringing it back to stable equilibrium. So in other words, any slight jostling of the system is just going to bring it back to the equilibrium point. That's why it's stable. If we look at the unstable point, this is where we have a maximum in the potential energy. Then the reason we call it unstable is let's say I place the object slightly to the left of that point. The force is going to be pointing to the left, so that's going to bring it further and further away from the equilibrium point. If I place it like slightly to the right of the equilibrium point, the force is going to be going to the right, which again is pushing it further and further away from that equilibrium point. So it's really hard to actually keep something at this unstable point because any slight disturbance is going to cause it to move further and further away from that point. Now, if we have neutral equilibrium over here, then there's no force at all. So the function, again, is completely flat, meaning there's no force at any point where it goes flat here. So that's what defines a neutral equilibrium position. Okay, so in general, systems are going to tend to evolve towards stable equilibrium. I mean, let's really think about that. If I place an object over here, it's going to want to end up over here because that's the way the force is pushing it. If I place an object over here, it's going to want to end up down here, again, where we have that stable equilibrium point because that's where the force is pushing it. You can literally think of this as a ball rolling down a hill. Okay, so if I place a ball at the top of the hill, that's unstable because any slight push is going to make the ball want to go down this way or that way. And where the ball tends to want to hang out is at this lowest point. Okay, so that's something we can generally say is that systems tend to evolve towards stable equilibrium where the potential energy is at a minimum. And so we have a nice physical picture here of what that looks like, okay? Imagine a cone. How would I put that cone in a stable equilibrium position? Well, I would basically put it this way, where the flat part of the cone is on the table. Okay, it's stable because if I sort of disturb the cone a little bit, I push it around, it's just going to go back to that position, right? On the other hand, unstable is where we try to balance the cone on its tip. So if I slightly disturb this setup right here, it's going to make the cone knock over. On the other hand, neutral is this situation where the cone is just sort of rolling around without any force acting on it at all. Okay, so that's just sort of an analogy we can make to this equilibrium position discussion. Okay, so let's do an example. Let's take the potential energy function that's shown down here. This is the potential energy of a particle moving in one dimension. It's given by x to the third plus x squared. What we want to do is find all the equilibrium positions, and for each one that we find, let's figure out if it's stable, unstable, or neutral. Okay, so the potential energy function that we're working with is u of x equals x to the third plus x squared. And so we know that at equilibrium, the derivative of that function is going to be 0. Okay? So let's calculate the derivative. We have the derivative of of x to the third. That's going to be 3x squared. And then we have the derivative of x squared. That's going to be 2x by the power rule. And we're going to set that to 0 and then solve for x. So let's kind of simplify this a little bit. I can pull out a factor of x, and then we'll have 3x plus 2. That equals 0. So there's sort of two ways this could work, right? If I have these two numbers that I'm multiplying together, and the result is 0, one way that could happen is x is equal to 0. The other way that could happen is if 3x plus 2 is equal to 0, in which case we'd have 3x is equal to negative 2, or x is equal to minus 2/3. Okay, so here, let's underline x equals 0, x equals minus 2/3 are the two potential equilibrium positions. So for each one of those, we have to test for stability. And the way we do that, using the second derivative. Okay, so here, we're going to take the second derivative now. of the potential energy function. So the first derivative is over here. That's 3x squared plus 2x. So the second derivative is just the derivative of that, which is going to be 6x plus 2. Okay? So here, let's test out x equals 0. If x is equal to 0, then the second derivative is 6 times 0. We're just plugging in that value of x plus 2, which gives us 2. So that came out positive. So that means the function kind of looks like this, right? It's concave up, in other words. And that means we're dealing with a minimum of potential energy, which, as we saw, means we have a stable equilibrium point. Okay, the next one we'll test is x equals minus 2/3. We'll look at the second derivative in that case. So we're going to have 6 times minus 2/3 plus 2. So 6 times minus 2/3, that's minus 4. And then plus 2 gives minus 2. The point is, this is something negative. So we have like a concave down shape, in other words. So we're dealing with a maximum in the potential energy, which means that point is unstable. So we found the two equilibrium points. One of them is stable, the other is unstable. And actually, we can kind of see how this looks if we plot out the potential energy versus x. What does that actually look like? So again, the function that we started with is x to the third plus x squared. If you actually plot this thing out, it looks something like this, where at x equals minus 2/3, again, that's where we have a maximum. That's our unstable equilibrium. And then right here at x equals 0, that's where we have a minimum in the function. That's where we have a stable equilibrium. Okay, so that's how this works. Okay, so I'd like to circle back to something that I mentioned before, which is what happens when we add a constant to our potential energy function. So the claim that I made earlier was that adding a constant to your potential energy function doesn't really change anything at all. It doesn't have any observable effect on the motion that you're describing, so you're perfectly free to add a constant and nothing changes. So let's try to see why that is using a potential energy diagram where we have, again, energy on this axis and then position on this axis. And let's start with this curve right here. This blue curve is what I'll call u of x. Okay, it's just a parabola. Let's say that's our potential energy function. And we can ask the question, what would happen if we added a constant to that function? So in general, if you add a constant to a function, if the constant is positive, you're moving the function up vertically like this. And if the constant is negative, you're moving the function down vertically like that. So let's say c is a positive constant, then we're moving the function up. And now this would be the curve for ux plus c. So it's the same exact curve, just moved up a little bit. So the question then becomes, do we change anything by moving the curve up a little bit? Well, the forces we're describing certainly don't change, because remember, force has to do with the slope of this curve, and we're not changing the slope by just moving it up. For example, the slope right here on the red curve is the same as the slope right here at the same position on the blue curve, right? So forces are not changing. Also, equilibrium points are not changing. On the blue curve, you see at x is equal to 0, we have a stable equilibrium position because the curve goes flat and we're at a minimum. Also, we have x equals 0 as a stable equilibrium on the red curve. So that hasn't changed either. So since the force we're describing and all the equilibrium points associated with it are not changing by adding a constant, we say that you're free just to add any constant to potential energy, and it doesn't change the actual motion that you're describing, okay? And another way of saying that is that you're free to set the 0 point for your potential energy anywhere you want, okay? So that's just another way of showing something we saw earlier. Okay, so next, let's talk about boundaries of motion. What we mean by this is that sometimes an object is restricted to move in a certain region. So there's like an X minimum that it can't move past. There's an X maximum that it can't move past. It has to stay between those 2 points. And the reason is basically it doesn't have enough energy to be anywhere else but between those 2 points. So there's a way of calculating the boundaries of motion, and it basically goes like this. The motion of any object is restricted to locations where the total mechanical energy, E, is greater than or equal to its potential energy, U of X. So before we go any further with this, let's just show why this is the case. Let's prove why this is true. Okay, so we'll start by saying the mechanical energy, E, is equal to K plus U. That's the definition. And we can rearrange this to say that K, kinetic energy, is just E minus U. We'll also remember that kinetic energy is 1/2 mv squared, and that's equal to E minus U. Okay, so to solve for V, we have V squared equals 2 divided by m times E minus U. So if I want to know the speed of the object, V, I would take the square root of that, and we have 2 over m times E minus U. Okay, so I want you to take a close look at what's inside of the square root. We have E minus U. If E is bigger than U, then we have a positive quantity in the square root. There's nothing wrong with taking the square root of a positive number, that's fine. If E is equal to U, then we have 0 in the square root. So basically V is going to be 0. That's what that would mean. But what if E is less than U? What happens then? Well, then we have a negative in the square root. What's the square root of a negative number? It's called an imaginary number. So that doesn't describe anything physical, right? It doesn't make sense to say that V is an imaginary number. Right? That's nonsense. So, in other words, this is not possible. It's not possible to have E less than U. So it must be the case that E is always greater than or equal to U. Okay, and that proves the result that E has to be at all times greater than or equal to U. So we can kind of look at this graphically. Let's say that this red curve is our potential energy, okay? And that this blue line is the total mechanical energy of the object. So since that's constant, we'll just show it as a flat line, right? Just one constant value throughout. So let's just take a look at, say, this region over here, okay? So in this region, the potential energy is bigger than the total mechanical energy E, right? That's not possible, so the object can't be located in this region over here. But what if we're over here, let's say? Now the total mechanical energy is greater than potential. That's fine, so we can be over here. There's no problem with that. But again, we can't be out here somewhere. So we're restricted, in other words, to being between these two positions. X min is what we'll call this, and X max is what we'll call this position over here. We're restricted to those boundaries. All motion has to occur between those two positions, X min and X max, because the object doesn't have enough energy to be anywhere else. It doesn't have enough energy to be here. It doesn't have enough energy to be here. Okay, and then one thing that we just showed is also that at those boundaries of motion, where E is equal to U, okay, where they intersect, in other words, those are the positions where the speed goes to zero. So the object momentarily comes to a stop at those boundaries of motion. The way you can think about that is, if I'm moving towards that boundary of motion, I have to slow down, come to a stop, and then move away. So right at that boundary of motion, we're momentarily coming to a stop. Okay, let's try to use this in a problem. So we have a block whose mass is 1.2 kilograms. That's this. And it's attached to a spring with a force constant, K, of 750 newtons per meter. The block is on a frictionless table and it's oscillating back and forth. So it's connected to the spring and just oscillating back and forth like this. Okay, at the moment when the spring is compressed by 2.5 centimeters, the block is moving at a speed of 0.45 meters per second. So at this moment shown in the picture, we know both the compression of the spring and the speed of the block. So based on that, we're going to calculate the boundaries of motion. Okay. So we'll start with this. The total mechanical energy of the system is kinetic plus potential, where the kinetic is given by 1/2 mv squared, and the potential, since we're dealing with the spring, is 1/2 kx squared. So since I know the value of v and the value of x at this moment in time that we're shown, I can calculate E. I can calculate the total energy based on that. So I have 1/2, the mass is 1.2 kilograms. The speed is 0.45 meters per second at the moment we're shown, so we'll square that. And then we have 1/2 of K, which is 750. Units are kilograms per second squared. And then X is equal to, well, it's technically negative because the spring is compressed, 2.5 centimeters. We want to convert that to meters, so we have negative 0.025 meters, and we'll square that. And if you do this calculation, what you're going to see is that it comes out to 0.3558. We have units of kilograms, meters squared on top, and seconds squared on the bottom. But we'll keep 2 sig figs on that. By the way, this is a joule. That's the energy unit of a joule. Okay, so remember we said that the object is going to be restricted to regions where E is greater than or equal to U. In other words, the total energy that we just calculated is always greater than or equal to the potential, which is 1/2 kx squared. So we'll rearrange that equation a little bit to say that x squared is always going to be the less than or equal to 2e divided by k. And if we square root both sides, you have to remember that when you square root, you have a positive and a negative root. So you're going to have a negative root for 2e divided by k and a positive root 2e divided by k. The way to interpret this is that x is in between these two roots. It's in between minus 2e divided by k and plus 2e divided by k. So let's just calculate what that is. What is, square root of 2e divided by k. What is that? So we have the square root of 2 times 0.3558. That's E. Units are kilograms, meters squared per second squared. And divide that by K, which is 750 kilograms per second squared. And what do we end up with here? 0.0308 meters. But we'll want to keep just 2 sig figs on that, so we'll round it up to 0.031 meters or 3.1 centimeters. So these are the boundaries of motion. We can move between minus 3.1 centimeters and 3.1 centimeters. So let's kind of plot that out. We have x equals 0. We have x equals 3.1 centimeters. And we have x equals minus 3.1 centimeters. The block is oscillating back and forth, but it has to stay between those two positions. That's what this means. Okay, so here's an example problem that I'd like you to try out on your own at home. What we have is a 0.475 kilogram ball thrown straight up into the air from ground level. So starting over here at ground level, y equals 0. And the total mechanical energy of the ball, E, is equal to 42.5 joules. Assuming there's no air resistance, what is the maximum height that the ball will reach? So you want to imagine that if you throw a ball straight into the air, it moves up, but it slows down as it's moving up. And at some point, it reaches a maximum height and then falls back down. We're trying to figure out what that maximum height is. So this is a problem that you might know how to solve already using methods from Physics 44, but it can also be done by thinking in terms of energy. So let's focus on this. The total energy of the ball is constant because there is no air resistance. So the total mechanical energy, E, is going to be conserved. So when we draw it on a graph, it's just a constant value. We indicate a constant value with a flat line like this. Okay? On the other hand, we can plot the potential energy. And in this case, the potential energy is just given by mgy because it's gravitational potential energy that we're thinking here. And this is just a straight line with a constant slope, okay? Because we're plotting energy versus position. Energy is directly proportional to y. So it's just a straight line with a constant slope. So what we said about boundaries of motion is that the ball can be located anywhere where the total energy E is greater than the potential energy or equal to it. So this region is totally fine. The ball can be here. But the ball can't be over here where the potential energy is greater than the total mechanical energy E. This is restricted. So we can find Y max by just looking at the point where these two lines intersect with each other on the graph. That's where Y max will be located. That will be the boundary of the ball's motion, in other words. So pause the video, see if you can work this out, and then we'll go through it together. So once again, we're going to be using the fact that E at all times is greater than or equal to U. And in this case, the potential energy U is given by mgy. Okay, so E is greater than or equal to mgy, which means if we solve for y, y is going to be less than or equal to, at all times, E divided by mg. So simply divide out mg from the previous equation, and this is what you'll get. So if y has to be less than or equal to some value at all times, then there's a maximum. Y max is just equal to E divided by mg. Okay, so what's E? Well, it was 42.5 joules. Joules would be the unit, but we can write this as a kilogram times a meter squared per second squared. Then divide by the mass of the ball, which is 0.475 kilograms, times g, which is 9.8 meters per second squared. So units of kilograms cancel out like this. Units of seconds squared also cancel out. Now, on the top, we have meters squared. On the bottom, we have meters. So one of those factors will cancel. So we'll be left with just meters, in other words. And you get 9.129 meters, but you'd keep 3 sig figs and round it to 9.13 meters. Okay, so that's it for this video. We're going to continue on with this lecture, and we'll finish Chapter 8 in the next video. But until then, take care. I'll see you in the next one.